All right, good day, everyone. This is Jason Straight with the Pass Cloud Virtual Group. Our presentation today is Azure Data Lake Design Patterns with Jason Horner. Before I hand things over to him, I have a few announcements I'm just going to run through real quick. First, this virtual group is brought to you and sponsored by Microsoft Azure, which works pretty good because we are a cloud virtual group. If you are not yet a member of the virtual group, I do recommend going out and doing so. You can do that out at cloud.pass.org. And out there's a login to subscribe. Once you get logged in, you can subscribe to the virtual group. And that gets you the newsletter that goes out to let you know when all of these webinars are scheduled for. It also lets you know if any webinar gets rescheduled due to any scheduling conflicts. Over the next few weeks, we have a number of sessions coming up. In fact, we have Jason Horner coming back up again here in just in about 3 weeks. We may adjust that because of a potential scheduling conflict, but that might go a week later. But we do have lots of other sessions coming up here over the next few weeks. If you are interested in presenting, there's always room on the calendar, so just reach out at cloud@pass.org or go out to the website, and on the website you can fill out a form. I'll get the details, and then we can work on getting you scheduled to present. This virtual group is part of a number of virtual groups that PASS helps to promote and support. These virtual groups focus in some cases on language, such as Global Hebrew and Global Italian. Others focus on different aspects of data platforms, such as performance and data architecture. If through the session you have any questions, please save them for Jason to answer here at the end. There is a Q&A panel in the GoToWebinar console that allow you to type in your questions, and then at the end of the session, we'll share those with Jason, and he can answer them for you. And with that, I will hand things over to Jason Horner for our presentation today, which is Azure Data Lake Design Patterns. All right, Jason, you are now the presenter.
All right. Hopefully everybody can see my screen.
Yep, it's coming through on the PowerPoint design.
All right, let's get going. So hello, everybody. As Jason Straight said, this is Data Lake Design Patterns, primarily based on Azure. I'm the presenter, Jason Horner. Here's the abstract. I'm not going to read this to you guys, but you can kind of look at it, make sure you're in the right session so I don't have to waste your time unnecessarily if you're not interested in learning about this topic, but hopefully you guys registered, so you already read this on the website. Welcome. This is about me, not really much to go into here. Feel free to connect to me on LinkedIn, follow me on Twitter, and if you have any more kind of in-depth questions or about kind of any of these technologies, definitely reach out to me via email. Always happy to help or give some pointers to the right resources. So let's get right into this and talk about some of the key concepts regarding data lakes. First, we'll kind of go into why do you need them. We'll talk through some data sources and types, different types of file formats that you might use or encounter. Talk a little bit about zones, which is the primary design thing that you can do with the data lake, and then talk a little bit about MPP architectures. So the big thing is, data is becoming ever increasingly important. And for those of you that are working kind of on-premise environments with SSIS, you're probably ingesting one or more file formats. Those could be CSVs, they could be fixed width, they could be all sorts of different file formats. And you're probably kind of already managing that data in some kind of a fashion. So you may be ingesting the file, processing it, and then zipping it up and rolling it off to like a file share somewhere. So you're kind of already using a data lake. It's just very ad hoc and it's not very, very scalable. But as the volume of data increases, we need new approaches to managing it. So if we think about data being the new currency, if I have a small amount of money, I can keep it in my wallet. If I have a larger amount of money, I'm keeping it in a vault. And if I have big piles of money like Jason Straight, I keep it in a bank, right? And so the data lake is really our biggest structure for storing data. Why is that? It's very inexpensive as compared to storing it in a relational database management system. And it's linearly scalable, it's very efficient for running large jobs off of, and it's a good foundation. One of the big benefits of a data lake is also schema on read, right? So I can ingest the data. Let's say I have a file format coming in and I only need to deal with 5 or 6 columns right now. I can run that file in. I don't have to do like third normal form modeling. I don't have to build a SQL structure or SSIS package, just ingest it, just copy it into the lake, put some compute on top of it, read the columns I need out of it for today. But then if the requirements change, as they always do, I can go back. I still have my historical files. I can reprocess that and bring in the additional data as those requirements emerge. So schema on read is a hugely powerful concept, and the data lake takes pretty good advantage of that, or more specifically, the MPP technologies that sit on top of the data lake. The storage requirements are key. So we want a very cost-effective storage. It has to be linearly scalable, and it has to have high performance. So just kind of talking through kind of some of these same points. With the data lake, we want it to be interoperable. I want to be able to interact with many different compute resources, whether that's a SQL data warehouse or Synapse, or it could be SQL database, Cosmos, any kind of system. It could be a Spark cluster. It's got to be very, very performant. So infinite scale, I should be able to support file sizes as large as they come, right? Different access patterns. So in addition to bulk reads, I might need to do smaller reads. I need to be able to efficiently write data in there. It's got to be secure. So I'd want to ultimately have some kind of role-based access control and some kind of access control lists. In the case of Azure Data Lake Gen 2, we have POSIX cycles. Also, it should be manageable. So I should have a scriptable API. I should have a management interface so I can interact with it, perhaps in the language of my choice, such as PowerShell or the Azure CLI, or just going directly into the portal. And it'd be great if I could have ARM templates to deploy these things. So that's kind of what I'm looking for overall in a data lake. So what are my options, right, as far as technologies on Azure? So the oldest option is Azure Blob Storage, or WASB, Windows Azure Storage. And it's an object store. And this is one of the first things to understand about the difference between Azure Blob Storage and Azure Data Lake Storage, whether that's Gen 1 or Gen 2. Azure Blob Storage is an object store, which means it's a flat structure. It means that every resource in there is not a file in a folder, but it's rather just a uniform resource locator. And so the big drawback with object store is that if I want to move a file from location A to location B, I actually have to rewrite that file out and then delete the old file, right? So it's very inefficient. Whereas with a file system, like a traditional Windows file system, I can update metadata, right? I can update the pointers to the files if I need to move directories, right? So if I need to move the folder from current to archive, right, or a file from current to archive, I actually got to delete and recreate the file. I can't just update a pointer. And so that has some performance implications. However, it's very inexpensive, and it's also optimized for unstructured. So things like our VHDs, our disk files that we mount from Windows virtual machines, or sorry, Azure virtual machines, our videos, our images, those kind of things is optimized for that. And it's very inexpensive. It's cheaper than Azure Data Lake Storage Gen 1 or Gen 2, generally speaking. And there's different levels of tiering, and so I can kind of dial back the performance. So I can use kind of a cooler tier for data that's accessed infrequently, or I can use a hot tier, and I can define different levels of redundant. Do I want it redundant within the Azure zone or the Azure region, and kind of those kind of things. So I don't have to worry about physical corruption. I still do have to protect against logical corruption. So, you know, the rogue ETL developer that goes in and deletes some files, I need to kind of come up with a backup schema for that, right? That data if I want to protect it. Moving on to Azure Data Lake Gen 1, this was Azure's first cut at this, and it was very interoperable. It worked with all the Hadoop Spark distributions. Its performance, so it's optimized for analytical file workloads. And whereas with WASB, or Windows Azure Blob Storage, there was a 2 terabyte limitation, or roughly around 2 terabytes, there was no file size limit. So I could work with arbitrarily large files. Not that that's a goal or a good thing, but it gives me that option, right? I have security. So with one of the things with Azure Blob Storage is I basically have access key, which means I can either access it or not, and I can read or write, but I can't fine-grain control the locations within it. With Azure Data Lake Gen 1, I now have POSIX ACLs, which are the Unix style ACLs of read, write, execute. And I also have Azure Active Directory integration. So I can use my principles defined in my Azure Active Directory, or my tenant, to provide secure access to that data. So that's hugely important for opening that up to business analysts and other people in the organization. And then as far as manageability, I have a folder structure, right? So I'm no longer an object store, I'm in file store, okay? So there were a lot of good things about Windows Azure Blob Storage and a lot of good things about ADLS Gen 1. And so when the team came together to come up with Azure Data Lake Gen 2, they kind of combined all those things together, right? So it gave us support for a hierarchical namespace that's on top of blob storage. It's flexible pricing, so it can be a lot cheaper than Gen 1, almost to the level of blob storage. Support for all sorts of authentication schemes, permissions, so on and so forth, and improved performance, right? So a lot of the, not that Azure Data Lake Gen 1 was inefficient, but there were some scenarios like copying lots of small files, dealing with kind of metadata operations that didn't perform as well as they could have. And so they fixed some of those performance issues, right? So those are kind of our three options. Generally, when I'm having conversations with clients, we recommend out of the gate that you use Azure Data Lake Gen 2. So that's kind of the design pattern one, is pick the right service. However, for some scenarios, right, if I need to have a staging area or I'm dealing with data that's unstructured, like binary, I might stage that data to blob storage first, or use blob storage for long-term archival purposes, just because it's so much cheaper, right? And the access patterns are a little bit different there. But generally speaking, if you're building a data lake on Azure today, you're going to want to go with Azure Data Lake Gen 2. Okay, and it's interesting. So you can kind of see from this diagram, which I shamelessly stole from the Azure Docs site, that we have blob storage on the bottom here. So all the things that come with blob storage, right? The object tiering, lifecycle management, the high availability, the zone redundancy, data governance management, all that stuff. And then with Azure Data Lake Gen 2, we build upon that a hierarchical file system, right? So it's a file system access. We've got our security controls that I talked about, the POSIX ACLs, and the Azure Active Directory integration. We've got the performance enhancements, so linear scalability, fast scanning for analytical workloads, and improved metadata management operations. And then the cost, the ability to scale the cost, right? And what's the other key concept that ADLS Gen 2 gives you, now that it's completely or mostly GA, is the fact that I can access it through either API, right? So they call it multi-protocol access. I can use the Blob API to do management operations, or I can use the ADLS API. So what that unlocks is a lot of the management scenarios and a lot of the integration with other services like Event Hub, Azure Functions, right? Azure App Services, all these different things. Initially, when Azure Data Lake Gen 2 went GA, it was only supported by some of the more kind of mainline analytical systems. And then as multi-protocol access came GA, now you've opened up all these other different access scenarios, right? So it's supported by a much wider base of clients, okay? So that in a nutshell is kind of an overview of the different options for building a data lake on Azure. Now we're going to talk a little bit about data sources, and we're going to talk about them kind of on two different spectrums, right? So the first thing is fundamentally, like, what's the inherent nature of the data, right? And so in a traditional ELT or ETL, so extract, transform, or load architecture, you have batch jobs, right? So every night I'm loading a batch, or every hour I'm loading a batch, right? And so I'm going to process that data as of that snapshot, bring in the new data, right? And time moves forward constantly, right? Another option is a micro batch, and this is something like Spark streaming, where it's almost near real time, but it's very, very low latency intervals, right? Like every 5 seconds, or every 3 seconds, or every 10 seconds, or every minute, and I'm grabbing that data, right? So something like Stream Analytics uses a similar pattern there as well. And then a true streaming system, something like Storm, where I'm actually processing this as the events occur, right? So this is as close to real time as you can get as a true streaming. So why I bring this up is because we're obviously going to use the data lake to store data, and the data could be coming in any one of these three formats, or you might have different sources. You might have a source that provides streaming data, such as like IoT sensors, and then a traditional ERP system that's providing the data in a batch mode. And so you just need to understand how that data arrives so that you can pick the best format for storing it, as well as the best ways to kind of manage it and move it through the data lifecycle. It's also to understand the types of data providers that you're dealing with, right? So there's a big thing in big data about structured versus unstructured data. That was kind of a huge kind of debate and all the rage, right? It used to be 5 years ago, all you heard about was all this unstructured data that's going to provide so much value. So what does that really mean if we unpack that? So in my opinion, when we talk about structured data, all that means is the data stored in a relational or tabular format, right? So it's coming from a SQL Server or Postgres or MySQL or Oracle or other database platforms. Now, we also have kind of this intermediate level, which I call semi-structured data. So these could be things like REST API that's returning JSON. So JSON has structure to it, right? There's schemas. They can be kind of dynamic. They can be different depending on the different sources, but there is a structure there. Things like Azure Functions or Azure Apps or NoSQL databases like Cosmos or even custom applications. They all could provide potentially semi-structured data providers. This could be JSON. It could be XML. It could be, data returned from a REST API. It could be all sorts of different types of interchange protocols. It could be via Kafka queue or a message bus, but those are all kind of semi-structured data providers. And then we also have event data. So things could come from Event Hub or IoT or Stream Analytics, and that's where we're looking at data that's kind of continuous. It's constantly arriving, and so we just need to take a sample measure, right? So, or maybe I'm just getting events, right? So let's say I have an application. Every time a new customer signs up, I get a new customer event from Event Hub. And so at some interval, I'm going to pop all those messages off that topic or queue and store that in my data lake. So it's just important to understand the context of how the data is coming and what the source system is that's providing it, okay? Now, one of the key questions is, okay, this data lake stuff is great, but how do I actually get data into the data lake, right? So the ad hoc way would be to use the Azure portal or the application Azure Storage Explorer, which is freely downloadable. Those are good for ad hoc copies or kind of one-time things, right? Then there's some shell utilities. So if I'm coming from a Hadoop background and I have an existing HDFS or Hadoop cluster, I could use distcp, which primarily copies files from a Hadoop data source into different targets, right? So that could be Azure Data Lake Gen 2, it could be blob storage, whatever. And that's basically just a copy utility. AZ copy is Azure's take on that. It's built for moving data efficiently between different Azure services. And then I have kind of what the next tier up, right? So I could always create like PowerShell scripts or shell scripts, bash scripts to automate distcp or AZ copy, but I want to operate at kind of a higher level most of the time, and so I'll probably look to an ETL or an ELT tool. So I could use something like Azure Data Factory, which I'm going to be talking about in March, or a tool like SSIS. Scoop is kind of a Hadoop-based kind of ETL tool. And then there's other tools out there that do ETL or ELTs, things like Apache Airflow, Talend, Matillion, Fivetran. Generally speaking, those are outside of Airflow, those are all things that you'd have to pay money for, but they offer some different capabilities. Alteryx is another one that's kind of out there, right? So you have these ETL tools that can move data in. You have script or command line utilities, right? Distcp, AZ copy, and then you have the portal or other applications, right? So those are kind of main methods of getting data in there into the data lake. Okay, and then if we talk a little bit more about data types, but kind of from a little bit deeper perspective. So we already talked about structured data, so that's relational, but we didn't spend a lot of time talking about unstructured. So we have things like our binary files, like our JPEGs, our PNGs, image files, video files. Now what's interesting about that is those too are structured, right? Every JPEG file, every PNG file has metadata associated with it in either the EXIF record, or there's data, there's structures, there's ways to process it, right? We can put image processing algorithms on it using cognitive services. So the key takeaway is unstructured data is kind of a bit of a misnomer. It just means it's not relational, right? There's no file format, right? So we could be storing, for example, photos of equipment that we're looking for wear and tear on, and then we're running that into the lake on through cognitive services or machine learning to identify what the equipment looks like in a good state, what does it look like in a damaged state. I may be trying to predict, is it close to the end of its usable life or not, right? From pictures. And there's all sorts of other scenarios for using that data. I could also be mining kind of textual formats. So like I could get PDF documents that I need to parse the text out of. I could get Word documents, and maybe I'm doing kind of bigram or trigram analysis or other textual analysis techniques just to kind of assess the sentiment of the document, or kind of understand the context, right? So there's a whole series of different text processing. So if you think about like engines like Elasticsearch or Lucene or Solar or some of those things, those are tools that you could put on top of a data lake to do textual analysis if that's what you need to do. So imagine you're a law office and you have like a huge corpus of legal documents, and you need to find every place where Java is mentioned in there. So you could do that would be an example of doing some kind of textual analysis, right? And then we have our semi-structured data. So those could be things like CSV, JSON, XML, other kind of formats out there, right? So as far as storage formats, let's just talk about text. So one thing that's really nice about text is it's human readable. There's no standard encoding, although RFC 4180 is the spec, if you will, for CSV. Different implementers follow it with different things. So if you've ever had the pain of processing a non-compliant CSV, you kind of know what I'm talking about. Things like having commas inside the text that you're supposed to have, or ragged fields, missing fields, empty values, any kind of those things can throw fits at CSV file processing. Non-standard encodings using 7-bit versus 8-bit ASCII. So there's many custom formats and encodings. You kind of have to deal with some of that, but it's well supported in general across the tool sets. You can use tools like Python, PowerShell, C#, any kind of code language to work with file that's in a text limited format. One of the downsides to using text though is it's in general you can compress it, but it's fairly sizable, right? As you start thinking through the data format. So you might want to, if you're going to be reading the text file a lot of times, you might want to look at a compressed file format, and we'll start talking about those in a few seconds. So we have JSON. It's kind of become the new hotness today. It's very interoperable. It's to some extent it's self-describing a little bit. It supports complex nesting, which can kind of throw fits sometimes for certain processors that assume kind of more of a flat or structured format. It's human readable, but the file sizes can be large without compression, so that can have some drawbacks as well. Avro is kind of the native format coming from like a Kafka server. It's got built-in support for schema evolution, so it's stored as a JSON schema and then a binary file. So the downside to using Avro in your data lake is you need a custom viewer utility to look at the data and figure out what's stored in there. But as far as like using Spark or some of these other MPP technologies to process it, there's a fair amount of support for Avro as a format. So sometimes you might use Avro as kind of your incoming format, and then batch up a bunch of Avro data and write it out to Parquet or some other format like that. So the next file format we're going to talk about is also a big data format, and that's Apache Orc. So this is a columnar format. I like to simplify things, think about this as like a clustered column store index. That's a little bit kind of a oversimplification, but it's got support for compression. It's got support for predicate pushdown. One thing to note about Orc is it's optimized really for working with Hive tables. So if you've got Hadoop or Hive, that's really where that file format's going to shine the most. Generally outside of those environments, you're probably better off going with Parquet. So Parquet was kind of a competing file format. It's kind of the default format for most data lakes. It's got support for compression, predicate pushdown, slower writes because it has to go through some different logic. It keeps statistics on the column segments. And this is kind of Spark's preferred format, right? So everybody understands that, for example, like Hadoop is based on MapReduce and uses Tez, and it traditionally is not an in-memory technology, although there's some enhancements there. Whereas Spark, the big performance boost from Spark to Hadoop is really the fact that everything happens in memory, right? And so Parquet is a file format that supports that. New to the scene recently is a format that was initially came out of Databricks, which is this Delta Lake. So it's now open sourced, and its main benefit is it uses Parquet under the hoods, but it maintains a transaction log. And so you have now support, like previously, if I was going to need to update data in a Parquet file, I'd end up having to rewrite out that whole Parquet file, which can be kind of inefficient. So with Delta Lake, I can actually do CRUD operations. So I can create, read, update, and delete in a table. It supports ACID transactions at the table level. So I can't support a transaction across tables, but I can support it within that table itself. It also enables time travel, which is kind of a neat feature. I can basically say, what was the state of this file as of this timestamp, right? And I can see the data at that point in time. So it's kind of a little bit like temporal tables in a SQL Server environment. And then it gives me, one thing that it gives me above Parquet is schema enforcement and the ability to support schema evolution. So Delta Lake's kind of becoming, it's getting a lot of traction. I don't know that I would use it for all data lakes, but certainly for some scenarios, especially real-time and streaming, if you're doing Lambda or Kafka architectures, I think Delta Lake's a good starting point. If you have data coming in that's highly transactional in nature and constantly changing, Delta Lake could be good. But if you're just getting, like, let's say every 5 minutes I'm getting data from an IoT source, or I'm getting POS data from point of sale data from a retail operation, I could just use Parquet because I don't need that data is immutable. Once it lands in the data lake, it's not going to get updated. So I don't need to add the overhead of Delta Lake. But Delta Lake has support in most of the big data distributions. So things like Hadoop and Spark will work with Delta Lake. It's a very simple code change to change from writing to Parquet to writing to Delta Lake. It's effectively just changing the output type. So the code's going to migrate over to that very simply. So one of the main takeaways from today's talk, other than kind of what is a data lake and what are the use cases, is this notion of zones. And zones isn't a crazy complicated topic. It's very simple. So it's basically using a well thought out folder structure to organize your data. And what zones really helps protect you against is this concept of a data swamp, which I'm sure everybody's heard a lot of buzzwords around that. So we're going to spend a bit of time drilling into zones. So in a data lake, you may have some of these zones, you may not have all of these zones. It just kind of depends. But I'll walk through kind of this in the order that the data will generally flow. So in some cases, you're going to have what's called a landing zone. The landing zone is really where the data lands effectively, and that isn't necessarily in your data lake. So an example of that is, let's say I have a third-party vendor that's sending me CSV files, and they're writing the data out to an SFTP server, right? That could be an example of a landing zone. So that data is getting written to that SFTP server, and then I'm going to process that data further. I'm going to pull it in with my ETL process. So one of the things that I think is a really important concept with your data lake is, if at all possible, you don't want random people writing data into your data lake, right? Whether that's other teams within your organization or certainly third-party people. So you always want to own the process that goes out and pulls the data and brings it into your data lake, or own that process. If it's streaming data, it's okay that it lands in the data lake directly, but you want to be in control of that process, because you don't want to get into a finger pointing game of like, whose responsibility is it to move here? You don't want to give people the access necessarily to write data to it, although you can secure that. So the landing zone may or may not need to be a part of your infrastructure. Another place where the landing zone comes into play is if you are using a Spark cluster or Hadoop cluster. They have this concept called the edge node, which is basically, it's a node in the cluster, but it's not participating in any of the distributed workload. So it's a place where you would put your ETL tools or your file shares, NFS mounts, or FTP files, or just a scratch area, right? But it's not actively acting as like a name node server or a worker node or a controller node. It's part of the cluster, but it's not involved in the distributed workload. So that's the landing zone. Then from landing zone, almost all of my data lakes and all the data lakes that you guys work with should always have this raw zone. And the key concept behind the raw zone is it's an immutable place to land our data in its initial format. So if I'm getting the data in a CSV format, I'm going to land that data into raw, and I'm not going to touch it. I'm not going to try to change the data types. I'm going to leave that file as is. It's a very simple ETL process to build, or data pipeline. The benefit it gives me is that, say a year from now, somebody comes in and wants to change the requirements, I have all that historical data, right? And so I can go back and reprocess things. So that's the concept of the raw zone. So one of the things you might say is, well, gee, that sounds really expensive. Like, I've got to store all the history of the data. But that's the main benefit of using the data lake. Like with SQL Server storage, comparatively, it's expensive, right? as opposed to just storing the data in a data lake, right? We're talking about, tens of dollars per terabyte or somewhere around that order. So it's key takeaway for the raw zone. It's very inexpensive, and you always want to store immutable data. You never want to update data in your raw zone. Now, it may be the case that you have data in kind of a custom format that's kind of not amenable to processing. And so an example of that is I worked ingesting a data file format that had a header record and then 0 or more children records in the same line that I had to break out and pivot those into rows, basically. And so while I could do that processing directly in Spark, it wasn't efficient to every time I need to go back and read the data to go back and do that transformation. So, or maybe there were data types where I got the data in a string and I want to convert it into a date time type for some reason, or I want to put different structure around that. So in that case, I could introduce this concept of a structured zone. I don't definitely need to have a structured zone, but it's a beneficial thing to add when it's called for. Then we get into stage and temp zones. So temp zone would be, let's say I don't get an incremental extract every night, but I get a full extract of my customer's table. So I'm going to dump that full extract into my temp zone, and I'm going to compare it to the file that I got the day before. And I'm going to generate an incremental file, and I'm going to write that out to my raw. So it's just a place where I can do some work, right? And one of the other things it can be useful for is when I run a big data processing job in an environment like Spark, it's going to create one file per each worker node or each thread in the job. And so I might get a directory full of different file outputs, and I might want to take all those outputs and combine them into a single file just for manageability or just to kind of satisfy like an OCD kind of thing. And so I can do that processing in my temp and then copy it to another zone, whether that's raw or whether that's stage. It's kind of depending on where you're trying to flow the data to. Which brings us to stage. So stage is the data ready to go into a downstream system. Now that could be a traditional data warehouse, right? So generally speaking, your data lake is not a replacement for the data warehouse. What I like to kind of make the comparison to is the data lake is really like a persistent staging area, right? So it's kind of in our Kimball architecture, it's kind of it can be a replacement for a staging area, but it's not a replacement for our data warehouse area. So what I could do is I could take some raw files that come in from different CRM systems and ERP systems, and I could run some transformation, cleansing, and enrichment, and stage that data out to a customer file that ends up loading a customer dimension in a data warehouse. And that load would come from the stage. And I could choose to do that ETL processing directly in the database, or I could use an MPP technology like Spark or Hadoop to do that processing, right? And that's kind of a simplified view. There's a lot that goes into that. But the key concept is stage generally doesn't store history. It's just the current snapshot that's ready to be loaded. It's staged to be loaded. And then the next area that you're almost always going to have is kind of this curated zone, and that's where if I'm storing data sets that are for a data science team, for example, or they're aggregated tables or they're flattened data structures, I'm going to store those in the curated zone. I generally speaking don't want my data scientists or my analysts in my raw zone or in any of these other zones. I really want to kind of restrict them to that curated zone. And so I've also seen architectures where instead of using stage, we just create a curated zone. I've also used the curated zone to create a data warehouse kind of replacement. It's not a great solution, but it can work depending on kind of what your requirements are. But generally speaking, like I'm a big fan of still using some kind of relational database to store your data warehouse. And then ref could be, let's say I get Tiger census file data or demographics data, things that occur kind of at ad hoc cadence that aren't going to be part of my normal ingest pipeline, or things that don't change, like a date dimension table, right? Things that I just kind of create a reference table. So I could put that in a reference zone. I could do a lot of other things. And then finally, a lot of organizations have legal requirements where they need to move the data out, right? So I could move data out of my raw or any of these other, or the curated zone, and into archive as a short-term holding place. And then when I'm legally obligated to remove that data, I could just delete it from the archive. But that would be a way to back it up. Now, one of the key things about data lake, and I kind of talked about this a little bit earlier, but you're protected against the data going physically corrupt most of the time, right? So Azure's not going to lose your data, but I don't trust ETL developers. They're very dodgy type of people, and so they make mistakes, right? They write bugs, or they have scripts that go bad. And so what I suggest that you do is, if the data is important enough to store long term in the data lake, you should have a backup plan around that, right? And so that's going to be governed around your RTO, so your recovery time objective. How soon do you need to be able to recover, as well as your RPO, to what point? Do I need to just go to the last day? Do I need to go up to the minute, right? And so those things are all kind of concepts from the database world, right, that we all know. But we need to think about, how can I store a copy of this data off somewhere safe that's protected, right? And so there's different third-party solutions out there. There's not really an Azure native solution that I'm aware of yet. However, what I have done is written scripts that copy the data out into another blob storage account that's kind of locked down, or another Azure Data Lake storage account. So that's an option there to protect you from logical corruption, not physical corruption. Keeping going here, so this is just kind of what I talked about at a high level. So I'll just spend a few minutes going through each of the slides. You guys can kind of read these, but this is just more for reference purposes. So structured zone, stage, our temp, our curated. Actually, let me go back to the temp. So one of the interesting things to note is, and we'll talk about this in the anti-pattern section, but the zones are subject to what's called the small files problem. So imagine you get a bunch of new customer records from Event Hubs or from Kafka. Those are going to be small files, right? Maybe 3-4K, if that, right? Well, generally speaking, MPP systems don't deal well with thousands and thousands of small files. Like I've had files with or directories with 40,000 files in them, and jobs would take 2 or 3 hours just doing all the file metadata management stuff just to read the directory. So what I recommend is that when you have the small files process, you kind of create a vacuum process. And what that does is, at some cadence, whether that's hourly, every 5 minutes, twice a day or whatever, you take and you list out that directory, you grab all those small files and you concatenate them into a larger file, right? And so you could change the structure. So you could be getting a bunch of JSON files and you could convert those into a Parquet summary file. That's an option too. But the key thing here is that the temp zone is a good place to do that, and just be aware that working with, on the order of tens of thousands to hundreds of thousands small files generally isn't going to be the most efficient or effective way of processing those data, especially for analytic workloads, okay? Curated zone, this is going to be very variable based on your use cases and requirements, but the key concept is the data in here is approved, it's blessed, it's been through the cleansing and enrichment problems, whereas the data in the raw data is going to have duplicates, it's going to have missing data, it's going to have data that hasn't been enriched, so it hasn't been cleansed, it hasn't been transformed. So this data is ready for the organization to use, okay? Archive, we talked a bunch about that. So it's interesting to note that generally speaking, I'll have my raw zone, and then for each subsystem that I pull data from. So let's just say, for example, that I'm gonna pull data from AdventureWorks, right? So my subsystem would be AdventureWorks, and then I'd create another folder within there called sales LT, sales LT for the schema, and then within that schema I may have a sales order detail. I'd create a folder for that sales order detail, and that's going to be kind of my folder structure, and I'll talk a little bit more about that in a few minutes, about how that relates to how I want to name my files and lay it out for partitioning. And then when I start talking about partitioning, what I do is, once I have that sales order detail folder, so I can point my big data solution at that sales order detail folder or the sales order header folder and scan all the files in that directory. So what's really important is that within a directory, generally speaking, I only include files of the same entity or the same content type, so it can be efficiently scanned. The other thing to note is that if the data volume is such that I do need to use partitioning, I'm going to want to partition that. And when I say partition, I'm saying create a folder for year, then another folder for month, and then another folder for day if I need to go to that level. If I need to go below that level, I can go to the minute level, second level. But what that allows me to do is, with my processing script, if I only need to process data from the most recent month, I can just process the data as a subset underneath those subfolders. So that's what's known as partitioning in kind of the big data world. It's very similar to SQL Server partitioning, except it's not managed inside of a relational database. It's up to you, the developer and the architect of the data lake, to come up with a partition structure. The other way I've seen people do partitioning is by geographic location. So it could be that you're running a manufacturing company and you have multiple instances of that manufacturing software in all of your different factories. So maybe you have 12 factories. So each system would be stored inside of a subzone, right? And then within that, you can further partition and basically kind of isolate that data, right? The other thing you might want to do is create a zone for users. So each user can kind of have their own sandbox where they can do experimentation or data science. And that gives them kind of a place where they're not going to hurt anybody, right? So there's some other zones that we could talk about. And then zone alternatives is worth mentioning. Databricks is really fond of using the bronze, silver, gold nomenclature. And the idea here is that the data arrives as bronze and then you're an alchemist. And so you're casting your Python spells on it and you're turning it into silver or into gold down the road. So the idea that gold, it kind of maps to curated, silver kind of maps to kind of our stage or our structured zone, and bronze would be our raw. So just, and lots of people come up with like cutesy ways to name zones, like kind of playing off the metaphor of the data lake. I'm not a big fan of that. I like the ones that I've kind of shown today, but you're free to build your own zones as they make sense for your scenarios. And then the biggest thing, which I've talked about, is the data lake's fine. Like, we've stored all the data, that's great. We've used ETL tools to bring that data in, but now what do we do with it? How do we access it? So generally speaking, you're going to want to put some kind of a MPP engine on top of that. And what all MPP engines have in common, as opposed to like SQL Server, which is a SMP engine, is that they scale out, they distribute the workload over nodes, and they rely on an executor or a controller node to coordinate that access. And what that gives you is that gives you your linear scalability to efficiently process large data sets. So we could use a tool like Databricks, we could use Azure SQL DW, now known as Synapse, uSQL, which is kind of more of a deprecated solution, but a lot of people probably have solutions built on that, or we could use Hive tables, Apache Hadoop. There's lots of other options too, right? So Azure Data Factory has mapping data flows under the covers that spins up a Databricks instance, so you're working with Spark. But the point is that the data lake's a great place to store the data, but in order to do anything with it, you've got to have some kind of a compute engine on top of that, right? If your data is small enough, then just load it into Azure SQL database and do some processing there. If you want to use Postgres, do that, MySQL, whatever. The point is that the data lake is kind of where we're doing a lot of the traditional ETL activities, and the relational database is where we're doing the querying activities, okay? It's a huge concept to understand. So let's get into some of the data lake design patterns. So we talked about zones as kind of the #1 pattern to kind of understand, and the need to use a zone. But how we name those files are important. So here's an example, right? I have sales order. Even though that sales order is in a folder called 2020 sales order 2018-01-12, I've still put the whole file name context on there as well as the timestamp. And the reason I did that is if those files get moved around somewhere else, I still kind of know what's inside that context, and I can still use that as kind of some metadata to intelligently process the files or not process them. If I only need to look at files from 2017, I can create a wildcard filter or a regular expression to just process files that match that certain pattern, right? So it's important. It makes the naming unambiguous and consistent. And we always want to use that format because it's sortable, right? If I go year, 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 month, month, date, date, it's sortable and it lines things up. Make sure that your casing is consistent. So it's important to understand that the data lake file system is case sensitive, right? So we want to have consistent casing. I don't care if that's Pascal casing or Camel casing or all lowercase, doesn't really matter to me. But just make sure that the naming things properly and kind of semantically is going to add a huge bunch of value to people trying to understand what's in your data lake. And we'll talk a little bit more about cataloging data and governance later in the session. Partitioning, so we already kind of walked through that, but not all files will need to be partitioned. For example, our customer file, we'll just put that in the customer directory and and that'll be it, right? And we'll just add the new files to it. But sales orders might be large enough, or it might arrive frequently enough with enough changes that it warrants putting them out in different folders. So it kind of depends on the grain you need, and that's based on the latency of the data and how frequently you get it. A key concept here is you want to avoid creating empty folders and zero-length files and mixing file types. Those are kind of some anti-patterns to look for and avoid. And the reason to do that is because you're just, well, it seems like a good idea, because if I create an empty folder, I at least knew the ETL job ran. But the reality of it is you're just making it harder to navigate and find the actual data. So I would advocate that you don't create empty folders or files. It's also important to understand splittability, and that determines how efficiently you can process the file. Imagine if I have a file that's 10 gigabytes, okay? If I'm in an MPP environment like Spark, ideally what I want to be able to do is load that 10 gigabytes into the Spark cluster and have each node in the cluster, let's say I have 5 nodes, each node work on a 2 gigabyte chunk and return the results back. If the file format isn't splittable, like let's say it's XML, XML is not splittable. I can't navigate into an arbitrary point inside the XML file and split it and get a coherent record. But things like single line JSON, CSV files with new line separators, Parquet files, those are all splittable, and so I don't necessarily need to store those in a format, or I don't need to think so hard about what's the proper size of this file. I can just kind of let it be. The flip side is if I'm using a non-splittable file like XML, then the ETL process should intelligently batch that out into like 1,000 records per file, right? Or some kind of heuristic there that's going to give me a large enough chunk. So generally speaking, the optimal size for a file in the data lake is about 128 megs, but that's contextual. So what I mean by that is that if the big data format, just like in a database where we format a file at 64K, same thing with big data. 128 is the size it likes to work with, but as long as it's a multiple of 128 and the file format's splittable, we can play with it, right? So I'm obviously, if I have 2 terabytes worth of data, I'm not going to create a bunch of 128 meg segments. Like, that doesn't make any sense. But what I might do is create a bunch of like 10 gig files, right? Or 100 gig files or whatever. So the key thing is to kind of balance it based on my processing requirements and the things that I know about the data. And the way to kind of come up with that is to do some data profiling and understand how much volume of the data am I getting on a day. Okay, compressibility. So sometimes if you put compression on a file, you can speed up the processing or reduce the storage costs. But the flip side is you could make the format unsplittable. And then just understand that some of those columnar formats like ORC and Parquet support compression internally. So what you just want to do is do some testing around turning compression on or off on the file format and see what that does to your workload. And just understand with compression, you're always trading off CPU time for storage, IO, and network bandwidth. So if you have a lot of spare CPU time and you have a lot of compute time, then compression is usually a good trade-off. If compute time is sparse, right, like I don't have a scarce resource, I don't have a lot of it, then I might want to not leverage compression. Okay, so just understand that when you're using those columnar formats like Parquet and ORC, they make a lot of sense for storing the data at rest, but they really make sense when you query that data multiple times in its format. Because they support column elimination, because they support predicates push down, they're really good for processing those analytical workloads. However, you're going to pay a little bit of a premium to write the file out. So you have to understand that if I'm just passing the data through for short-term storage, and I'm going to move that data into Azure Synapse, for example, I might just want to write it out to an uncompressed CSV because Polybase will load that very efficiently. Okay, so and the other thing I'll call out here that I've had to do specifically with SQL DW and Polybase is to work around kind of encoding issues with date times or inconsistent formats. If I store that file as Parquet as opposed to a CSV, I generally get some better behavior. It's more consistent. So that's something to think about as well. So anti-patterns, basically everything I talked about today so far are kind of the design patterns. So using zones, using the right file type, using the right type of partitioning, using the right file formatting. Data swamps are basically everything else, everything that doesn't do that, right? So if I use multiple file types in a single folder, I don't use good folder organization, inconsistent file naming. I don't have any data governance. The key thing is if I don't structure that data correctly, just like a relational database, nobody's gonna be able to make sense of it, right? So I'm creating the data roach coach, right? The data checks in and nobody can get anything out of it, right? It never leaves. So the swamp prevents self-service. That's the key takeaway, okay? And we're coming up on about 45 minutes. I've probably got about 15 minutes left of content, just as a time check for folks. With that being said, small file problem, we already talked about that. The concept here is when I get lots of little small files, I want to create a process that concatenates those all into a larger file, okay? Because processing multiple small files impedes efficiency and causes additional latency and storage costs, which are processing costs at the end of the day as well, right? Optimal file sizes, so I talked about that magic 128 meg number, but based on what your big data processing engine is, so if it's Hadoop or if it's Spark, and whether it's an org file or a Parquet file, that's gonna, and what version of those distros you're using is gonna control kind of what the most recommended file size. So the best thing to do is read the docs and figure that out, and then do some testing to verify. That's super important as well. So this is just kind of some common challenges. I'm not going to read all these off to you guys. I assume everybody can read. But what I will talk about is kind of what I think are a couple of the main points here. And so one of those is anybody can create a data lake, right? I could sit down with anybody on this call right now, and in an hour, we could set up a data lake, or probably less than that. We could start moving data into it. But without governance, without access control, without understanding that data, it's not going to get used, right? Or users will be frustrated. So it's important to put some governance in place around it. Who can access the data lake? Who can read? Who can write? Where can they do that? What's the process for requesting access? And then also understand that a data lake may not be the best way to integrate data that's already relational. If you're moving data out of an on-prem SQL server, and your goal is just to create a basic data warehouse, it may not be necessary to dump that in the data lake, right? But if instead of that scenario, if I think about a larger enterprise data warehouse where I'm not only moving data out of one source, one relational source, but I'm moving data out of REST APIs and other third-party softwares, and I have multiple instances of different systems, and I need that kind of integration hub, then the data lake is going to make a lot of sense, even if most of that data is relational, right? Because it gives me a place to kind of store the data. And it also offloads some of the load from that source system, right? So I'm not always having to go back to the source to re-request historical data. And in some cases, systems will age the data out, right? So I may be working with a system where, you know, every year they're taking last year's data offline, right? Because the system doesn't perform well with historical data, or there's a compliance reason that they're doing that. And then just understand that the data lake isn't a replacement for a relational data warehouse. It's not meant for that. It can support data science and self-service scenarios, and you can put Power BI directly on top of that. But generally speaking, you're going to get your best results if you build a proper dimensional model, right? And then don't just accumulate data just to accumulate it. I mean, requirements are going to change, so you don't know what's not useful today or not being used today might become critical tomorrow. But just kind of go back and check and make sure that data is actually being used, okay? So really the key thing here is governance, and there's really three things, in my opinion, to that. One is metadata for lineage tracking, having a data catalog, right, that can tell me what the data source is, what's the data dictionary, and then putting some data governance in place, right? So data governance is very much a verb, not a noun. So it's the act of doing something. It's not just saying, hey, here's this document that outlines our procedures. You actually have to follow through on that, okay? So Azure Data Catalog is a kind of MVP, so minimally viable product for data cataloging. It has a lot of things that it doesn't do very well, but I still recommend that people at least get started with that, especially for their first data catalog project. Even though it's not really being actively developed right now, it's still a good place. It still gives you the search and discovery capabilities. It allows you to document things, so you create an online shareable data dictionary. It's very inexpensive, and it has some other capability like tagging, the ability to set up URLs to request access for data stores, things like that. So there's still some value there. And then the data catalog is really addressing these kind of governance questions, fitness. So can I use this data? Is it going to be fit for my purpose? Compatibility. Can I join this data with other data? If so, how? Right? Knowledge. So who's the expert in this data? Who knows this ERP system? Who can I go for help? Access. So who can let me in? Lineage. Where does the data come from? Right? And then quality. Can you trust this data? So these are all kind of pieces of governance that you as an IT or a data engineer need to work with and kind of come up with this source, right? And decide how you're going to do data governance on your data catalog. But it's hugely important that you do something. And then when I go through the process of taking data from files and putting them into a structured result set, so like a table, I'm going to track metadata. So when the file, what was the file that it came from? That's the first thing. When was the file created? When did the file get processed? And I might generate an MD5 hash. Why? Because if I go in and a user points into some data and says, this data looks bad, right? I now know, okay, this data showed up in this source, and here was the MD5 hash. The first thing I'm going to do is go to that source file and see if that hash matched. Did it get corrupted or overwritten? If it did, that helps me know where the problem was, right? The problem wasn't necessarily a bug in my ETL process. The problem was that the file got updated, but the database didn't, right? So it just kind of gives me some breadcrumbs or traceability back to understanding why the data is in the state that it's in, right? And these are common columns, process date, created date, who did the updating. Those kind of things are common in relational databases as well. So nothing new there. And then just really quick diving into some security. So in order to start giving access, one of the main ways to give access into an Azure data lake is to use our security principle. In Azure, those can be one of 4 types. So users and groups, those are all principles. Those are just our Active Directory users and groups. There's this concept of a thing called a service principal, which is an application registration that has a key associated with it that you can use to authenticate that says, hey, here's the key and here's my identity, let me in. Or managed identity, which is my preferred approach if the service supports it. And it's basically the equivalent of a service account for a service. So we'll dive into those. So service principal, in this case, I've created a service principal called ADF DPSP. That service principal has an application ID, right? That's a GUID. It has a directory ID or the tenant, the Active Directory tenant, and then it has a key, which I'm not showing here. And so if I provide the application ID and the application key, that's giving me basically a user ID and a secret to authenticate with. And so the resource can let me in if I have the rights. Okay, it's also known as an app registration. So I, generally speaking, service principals are better than like dedicated user accounts, but you still have to manage that key or that secret. So the solution to that is managed identities, or formerly known as MSIs, or managed service identities. And this allows me as a service, so me as Azure Data Factory, or me as this function, right, to authenticate with the store, so data lake or SQL database or whatever. So this is the preferred method. Why is it preferred? Well, because we're not managing a password. It's basically just saying, I'm this Azure Data Factory, or I'm this VM, let me in. And there's no password associated with that. So I don't have to mess around with storing a secret in Key Vault or introducing the risk of checking in a secret into a source control repository. It's inherently more secure because I'm depending on the identity of the service, not on a secret being managed appropriately. Okay. And then this just shows where in ADF, for example, where I can get that application ID. So some other stuff there. The other types of access you can do are by access keys. And so the first thing we'll look at here is a storage account key. This key here opens up the entire container. So anything that's in that data lake storage is, if I have one of these 2 keys, I have carte blanche access. Okay, so this is not an advisable way to authenticate, but for blob storage, it was kind of one of the only options. Another thing you can do is a shared access key. So this is a little more granular. I get a what's called a SAS connection string, which is basically a URL that's been encoded with a begin and end time, so I can control the expiration of it. I can force whether it's on HTTP or HTTPS. I can set what am I allowed to do. So can I read, can I write, can I delete? I can set what resource this is allowed on. So I can do it only on an object, or I can do it on a container. And then I can specify the service. So do I want to do it on the blob service, the file service, queue service, table service? So just understand that a storage account can offer any of those 4 services, but really what we're talking about in the scope of this talk is really just the blob storage. Okay, and that blob storage may or may not have hierarchical namespace enabled. So shared access signatures, if your resource doesn't support for whatever reason service principal authentication or managed service identity. So obviously managed service identity is our first option, and then we fall back to service principal, and then I would say shared access key. And if it doesn't support shared access key, then you're back to a normal access, or sorry, shared access signature. Then you're back to a normal access key. So that's authentication. Role-based access control is super important to understand. These roles are all built into every Azure resource. Owner gives you full access. Contributor gives you everything but the ability to manage access, right? So there's no huge difference between contributor or owner, except if I need to go and assign and say, hey, Sally can access this resource, I have to be an owner, or I have to have user access administrator. Reader just allows me to view the state of it, but not make any changes. So those are all standard Azure resource roles. You can also create your own. We're not going to get into that. There's also resource specific roles. So if I've got storage blob data owner, which allows me to do everything I want to the data inside the container. It'll override the POSIX ACLs that are set within the container itself. So understand that these Azure role-based access is really talking about the outer resource itself and not necessarily the data within it. So an example of that would be in a SQL server. If I give you role-based access control to the SQL server, you might be able to set firewall rules, you might be able to create databases, but that doesn't mean that you can actually go into the database and access the data, right? So we still rely on the SQL Server database permissions so to give access to the data. So just like that, if I give you contributor to a data lake, it doesn't necessarily mean you have access to the data inside. So then I could assign you storage blob data owner. It's going to map you to the super user, which is basically the SA concept inside of the Azure storage. Storage blob data contributor gives you read, write, and delete on the blobs underneath. So this is an alternative way to give access without messing with the individual POSIX ACLs, which are not complex, but a little bit more cumbersome to work with. And again, if I only want to give you read access to everything in that blob container, I can give you storage blob data reader. These are role-based controls that are specific to the Azure Data Lake resource itself, or the Azure Storage Account resource. Access control list, so when I get inside that data lake, now I have this dialog, which looks very familiar. And then basically I can say owners, right? They have read, write, execute, or I can explicitly assign, like I can say Sally can read, but cannot write, or I can say Sally can execute, right? So I can do some Unix kind of file permissions here, right? So this is just a synopsis of what those are, right? So if you want to learn more about this, there's plenty of resources on Unix permissions. We're not going to go into that. But just note that this is a little bit different than Windows permissions. So some of these scenarios, the key thing is in Windows, I could give you access to data.txt within Portland, Oregon folder hierarchy, and you could read and write that file. But within Data Lake, I need to at least have execute all the way down the path. I need to have an unbroken chain down to the thing that I want to work with, and then the explicit writes on that file. That's the key takeaway from this. But just different scenarios here in case I want to list, or if I just want to read, or if I want to append data, or if I want to be able to delete it, different privileges are needed, okay? Firewall, so I have the ability to turn a firewall on and off. I can also enable a private endpoint. So that's pretty much it. I think we're already at about an hour. I'm going to turn it back over to Jason and we'll do some Q&A. And if we don't have time to answer your question, or if the question's kind of long and we can't kind of answer it in this context, feel free to send me an email here and I'll get back to you as soon as humanly possible. So with that, Jason, do we have any questions?
We do have a few questions.
Okay.
So let me start with this first one. Okay. Would you be able to show or share best practices for ADLS container/folder structure?
Yeah, so that's hilarious. I can do such a thing, maybe. So here's my take. So this is Azure Storage Explorer. Hopefully everybody can see this. So inside of this is an ADLS Gen 2 thing, and inside of here, notice that when we're looking at security, I can define a file share, a queue, a table, and a blob container, and I have multiple blob containers in here. Now, these don't share the underlying storage; they share the storage account, but I can't, for example, create data in a blob container and then view it in this file share, right? So these are isolated file systems, let's say. Then inside of here, what I generally do is I'll create a container called DLS, that's data lake storage. And then inside that data lake storage, here's where I start creating my zones, right? So I've got raw, I've got curated, I've got some of these. And you can see as I go in, hopefully, it's going to take a little bit while. There's my AdventureWorks LT, sales LT. So that's database name, or it could also be server name, database name, schema. And then within that, I would put my tables in here, right? And then I'd go into my partitioning scheme. So that's kind of the structure, but it is in some ways like it's very, very simple, but it's very, very complex, right? It's very simple because everybody understands, I would hope, folders and files and such, but the organization is really where you're adding the value, right? And so the real answer to that question is this is what it would look like from an implementation standpoint, but it's all those slides where I talked about the zones is really the devil's in the details, right?
All right. If you were to bring in structured SQL Server data or structured data like SQL Server, what's the process for maintaining history and what file format do you use?
So it's a great question. I've got a couple different options, right? And so some of it depends on how I'm going to get that data in there. So I've done a couple different cuts at an architecture to do that, obviously, because it's pretty common. So one option would be to, and I do this probably for a variety of reasons, but I might want to just use push replication to an Azure SQL database and replicate those tables. Now, obviously, I got to understand the volume involved and the loads and so on and so forth. I would replicate that to a database. Inside that database, I could put change tracking on those replicated tables. So I'm offloading the change tracking workload from the source system. And in some cases, that source system's not under my control. Like it might be a third party. So they're not going to want me to turn on CDC or change tracking or anything like that. Once I get those change feeds, then I can dump that data out to my data lake for long-term historical retention. And then I can also then continue to process that data in that database into my data warehouse. So that's one option. Another option is to send that data to Event Hub or to a Kafka queue and treat the data like a stream of changes, and then just persist that data into my raw zone. It's probably going to come to me as either JSON or Avro, and then I'm probably going to write a process to parse those out. The manual way is to use a traditional kind of ELT approach, and I'm going to go in and write either an ADF pipeline or an SSIS packages to go in and extract the data from the source system. So let's say an example where I can't get a delta for some reason. And so when I say delta, it's just change, right? I just have to go get the whole table. So I go grab my entire table. I write that out. I'll probably, by default, probably use Parquet or CSV as that destination file format. And then I'll compare that with my last snapshot and manually generate the delta and move that into stage and load that into my data warehouse. So for efficiency purposes, right? Because it doesn't make any sense. It's super expensive for me to load 100 million records, the entire history of the table, when only 2,000 records have changed or been updated, right? Inserted or whatever. So I want to work those deltas out in the data lake using big data compute like Spark or Databricks or something like that, if possible, right? So anything else?
Yeah, sorry, I muted myself.
No, that's
fine. Let's see here. If small files are a problem, would you still recommend to have a structure of year, month, date, hour, minute, second in a data lake folder structure?
So again, that's going to depend on the size, right? So I've worked on systems where we've generated gigabytes of data a second, right? So think about a large real-time network monitoring where we're trying to detect port flapping or something like that, like network activity patterns or malware. Imagine a SQL Server environment with 1,000 SQL servers, and I'm doing database audit, and I need to store that data. Or imagine, this is a use case I actually worked on for a client where they had a huge tier 1 SQL server, and they basically wanted to know everything that touched, every query that went against SQL Server, they wanted to capture it and mine it for patterns, right? And so, as you know, like if I turn on an extended events trace and grab all the queries in a high volume SQL, I could easily generate, you know, a gig or 2 gigs worth of data in a second, almost enough to bring down SQL Server if it's not done correctly. So in those kind of environments, then you absolutely want those more granular partitionings. But if I'm only generating, like, say 10,000 records a day, I might just create a daily folder. Or if it's super small, I might just create a monthly folder, and I'm going to store 31 or 29 or 28 days worth of monthly data inside that folder. So it really depends on the latency and the volume of the cadence of the data arrives at, right? So I know I probably kind of waffled around a little bit, but I didn't mean to imply that every partition structure has to go down to that second or minute granularity. You pick the granularity that makes sense, and if that's monthly, great. It could be yearly. It just depends on the size of the file. What you ultimately want to do is to arrive at a file size that gets you that balances the number of files versus the size of the file, right? So it's always a trade-off. I don't want 20,000 files, but I don't want 2 files at a terabyte each either, right? So I've got to find a balancing act somewhere in there.
Great. Let's just do a couple more here. Is it simple to build historical staging table for point-in-time querying?
So if you're using Delta Lake, it's absolutely simple, right? It depends on how that data arrives. So if I'm basically what I'm doing with most data lake architectures, if I'm using a raw zone, is I'm kind of creating that temporal version of that data set. But the key thing to understand is it's not transactionally consistent with the changes at the source system. It's going to be consistent, well, depending on how I pull it. But if I pull it at an hourly cadence, I'm just getting that snapshot as of that hour, right? So that data could have changed in the interim window there, or it could have been updated, deleted, and then reinserted, and I wouldn't catch that, right? And so that's the main difference between a technology like CDC, which gives you the full history of the changes, versus change tracking, which just gives you the current state, right? And so depending on how you're extracting that data and what mechanisms you have available to at the source, it's either a very easy thing to do or a very difficult thing to do.
All right, and this will be the last one that we do here.
Okay.
Can you use SQL Server replication to replicate to ADLS?
Ooh, I like that. That's actually an interesting idea. So you can't today without some other intermediate technology. What I would recommend that person do is go to the ADLS. There's a user voice or feedback site. I don't have the URL off the top of my head, but go in there and add that as a request. It's probably a long shot that they would implement it, but it's an interesting concept to me, right? Because I have to write a lot of plumbing, and we've automated that, right? So I can basically go into a database with 1,000 tables, point my script at it, generate the replication, and then generate the pipelines to process it, right? It's all metadata driven, and I can't share that with you guys just before the questions start coming about that, but it's easy to do. Well, it's not easy. It's not terribly difficult to do, right? It just takes a little bit of elbow grease. But there is no way to replicate directly into Data Lake. But like I said, you can replicate into a Azure SQL database and then put change tracking on that and hook that up to an ADF pipeline and pull it out that way. Or what you probably really want to do is use either Event Hub or Kafka and then publish those changes out to there and then process them from there as kind of like a message. So with that being said, if that's the last question we have time for, if there were other questions, Jason, if you want to kind of send them to me, I can
I'll
go through
send you
and
the
kind
full
of
list.
post them on it. And then if you didn't get your question answered, feel free to ping me on Twitter or email me, and I'll try to respond as quickly as I can.
All right. Excellent. Well, everyone, thank you for attending here today. And the one did come in just now that I can answer. Will this be available on View? Yeah, I'm going to probably upload it to the site at cloud.pass.org to the meeting archive. probably sometime later this week, probably Thursday when the second session for this week is done. So Jason, thanks for presenting. Can't wait for the next session.
Yeah, I'm excited, and definitely if you have kind of those questions about how to move the data around, that ADF session is going to open a lot of that up to you guys and kind of show you kind of best practices for processing that and doing deltas and things of that nature. So I think it's a good complementary session to this one. So look forward
All
to
right.
doing that and see you guys in March.
All right. Thanks and goodbye, everyone. Have a great day.